Okay guys, I'm going to give a look here at doing the 2019 higher level short questions. So, the first question here was the dihedral angle between ABC and BCD. Now, I would strongly recommend that you use a colour to identify the dihedral angle. So BC is on both planes. So BC is the line that's on both. I'm going to just try and colour that in blue there to make it a bit easier to follow. Okay, so that's the line of intersection. So what we want to do is take an auxiliary to get a true length of this. So I'm going to put an XY line just out here, project true length of the line of intersection, and just bring a point from each plane. Okay, so just adjust that. So I'm projecting from here, so it's from the last XY line back. So I need to have my distances, which are heights in this case, for, I'll start off with B and C. No, that is the true length of the line of intersection. Now I know it would be quicker to bring more points, but I want to try and just explain it as I go along as well. So that is the true length of BC, which is the line of intersection. Now the next move, so I'm going to do this in two steps. I'm going to find the point view of that now next by looking along it. So when you look along a true length, you will see it as a point view. And now, since I'm projecting from this view, from the last XY line back, is where I'm taking my distances. So that's why both C and B are the same distance back. So when I look along the true length, I will see a point view there of, I'll put that in as a green dot, that is a point view of the line CB. Now, what I need now is 1 point from both of the other triangles. So we have true length, point view of them, so I need to get B now. Okay, so B, sorry, A. Which is here. And I was also bringing D. So here's A, there's D. And now when I project these along at the same angle as I went to see the point view, A has to be on that line, D has to be on this line, and again the same rule applies. I am projecting from here, so it's from the last XY line back is where I'm getting my distances. So A is this tiny distance here, and D is this distance, and my dihedral angle now this is A, that's D, so that's an edge view of CBD, and that's an edge view of ABC here. So my dihedral angle is this angle here. Now the second part of that question again, I'm going to try and use some colours to help people understand it. It says draw the elevation and plan of a horizontal line on CDP that goes through P. So a horizontal line on that triangular plane there that goes through P, that has to be a horizontal line in elevation, and I'm going to call this X, the other end of the line. So it says there then, determine and indicate in degrees the inclination of this line to the vertical plane. Okay, now the vertical plane is coming up here, so we've got to find that in plan. So when I project down X, here's point X on the DC line. There's point X. That is the horizontal line looking down on it, but we know it's horizontal, and we want to know the angle between that and the vertical plane. So if I extend that in and just extend over the vertical plane there a little bit, so this here degrees is equal to about 25 degrees. Okay. Now obviously you would be measuring that with a protractor, and that is the first one done. Now the second one, this hyperbola, you've got the Directrix DD, you've got the axis. Okay, so I'm just going to label this. Here's our axis. Here's our line for eccentricity. So there's the eccentricity. Now it says the drawing on the right, Directrix focus eccentricity, and a few points are found. But anyway, once you've got the eccentricity and the focus, you're in business. Autopilot should kick in immediately at 45 degrees from the focus to hit the line of eccentricity and down, gives us the vertex always. And gonna just take a few ordinates. I'll take one there. There's that's another method of doing it there now. I'm gonna just take those ordinates through these points. So now the line of eccentricity is a mathematical line. So the eccentricity, so the distance from the point to the focus over the point to the directrix. So that is the distance from the focus for that ordinate. Now we're only drawing the top half of it here, because if we were drawing the full curve, we'd be going underneath as well. Now we know, or hopefully we know, that the line of eccentricity is always a tangent through the line going through the focus, which is called the latus rectum. So that is the point there, because that is the distance from the focus. So if I even took that and swung it from the focus, like it gives me that point P. So we know that. So that's the distance from the focus on that ordinate. That is the distance from the focus on this ordinate. So you will see that that point has already been found. And finally this one, again, I know like that this is found, but I just want to go through the method. So there are all the points that I need on the curve. So I'll just put the curve in here in color. Make it a small bit easier to see it. Okay, and as I said, they're normally like that's just the top portion of that. So that's our hyperbola, because if you have the eccentricity and the focus, then it's always 45 degrees and down for the vertex and so on. Now, the second part of this there, then it says, draw a circle that will be tangential to the directrix and also tangential to the hyperbola at point P. Now that is, I wouldn't call it a trick question, but there is one specific piece of knowledge that if you know, and I spoke about it earlier, and that is that the line of eccentricity is always a tangent to the curve at the point above the lattice rectum. I will just label that here L or lattice rectum. So if you know that that's the tangent at that point, it means that the center of the circle is going to be on the normal, which is 90 degrees to that. So basically all you have to do is go off here at 90 degrees. I'll just mark that there just so people see what I'm talking about. You're going off there at 90 degrees, and if it's touching this point and it has to be touching the directrix, we're going to have to bisect that angle. So I'll just do that with the compass. So bisecting an angle, the bigger the better. So just step out 2 distances there and 2 more equal distances here. And that bisects the angle. That's the line that bisects the angle. So this here has to be the center, and I know that the other point of contact has to be here. That has to be the other point of contact. So if I set my compass to there, touching at P, so there is a circle tangential to the directrix and also tangential to the hyperbola at P. So there and there. So that is that one done. Then okay, so here's some interpenetration. You've got the plan there of a building, and again there, if you struggle about these, I would be a fan of maybe, you know, maybe coloring in some of the objects there. No, it may not be ideal if you're stuck for time, but I'm going to just stick a few colors on this there to help people to visualize this. So you've got like that yellow ABC building going through here. So now considering that I'm going to just draw a person here, their hat and their left and right feet. They're standing looking in at that building. So B is at the front. So that's where B goes in. Now, because B is at the front and nothing is going to stop me from seeing that, I can heavy that in. And then C goes in here. So I can just project that up. And that's the definite, I'll just heavy in that point, that's the definite penetration point there. Now, if you're standing, we're looking down from above here now on the plan. If you're standing looking in at that, you can't see A because that is around the back. So, that is where A would be. Okay, and all that is going in on one vertical surface here. So that's just dotted line, which I can see, and that would be then just the front view of that triangular prism part of the building. Okay, so again there's only benefit to putting some color on this is to help understanding. And I'll just do the same there with where it comes out at the other side or passes through from the other side, so I'll just stick a quick color on that. Okay, so again there you've got all the elevation. So we want to complete the plan. Now the easy point here being C, I would say, because that's on here. So just bringing down C from the top, and we know that this is C coming over here. So that there is definitely where C goes in. And B and A are in line with each other here. I'm gonna just write this down there, that both B and A, and that's C up there. So both B and A pass in here. And because that's horizontal there, that's going to be a dotted line running along there underneath for that running across there is my dotted line. Now what makes this just a little bit tricky there is the change in angle, okay, because one part of the house is sloping up here and then the angle changes. So to find that, you could use an in view, but you don't really want to because it would be too slow. But if we projected this height over here, just put an arrow on that, we could bring that height out to the sloping surface, bring it down, and I can project them then back in because this is horizontal. So that's coming back in and back in. Down from here. So there. And here. And that goes up to the top to C. Back down on the other side. And then, so that's sloping up in that lower slope surface up to there. And up to here. And I'm going to stick a bit of color on that. Now you don't want to go colouring inside in the exam on this. You absolutely have to understand it because it's too slow, but to help understanding here, because we're doing this just to learn. So now the next thing it says there is they want the true shape of the triangle ABC. Now ABC is here now. How to do that, or more so how to do it quickly, I guess, is the thing. Now one of the immediate ways that I would consider doing this anyway is kind of like the junior start graphics question there, by rotating ABC around. So if I was to rotate ABC around, so I'm swinging it all around point A. So we're not moving A, but we're after hinging but the heights don't change. So that is the new position for C, and the new position for B, call it B1. So we never moved A, so A stays there. Okay, and this here, that there is the TS for true shape. Now, another way, if you know your geometry, another way I could have done that, just to look at another way of doing it, is I could have just rebatted and knocked down that triangle there. So if I just knocked down that surface there, well, I don't even need to move A and B. I could do it like an auxiliary, or I could rebat it. I'm actually going to leave A and B right where they are. And again, the height of C, that is a true vertical height there, because that is a vertical surface. That ABC here is a vertical surface, so I can just take the height of C here, and because that's a vertical height, when it lies down horizontal, it's also a true height. So that is the actual height of C, and just call it C1. So that's another way that I could have got the true shape of that as well. So just put a TS here for true shape. And that's another true shape there. So that's two ways that I could have done that. Then on to this perspective question. So what you have is a hurling pitch, and I suppose the one thing I would notice here immediately is here's our vanishing point for all those lines. So I'm just going to extend in the far sideline. So here is the near sideline, and because the far sideline is parallel to that, it has to be going to here as well. So I can immediately then vanish the 21 for the GA people, but this line here and the 14, okay, so this would be the 21, so I can begin to heavy this in here now. Just stick it in colour to make it stand out a bit. So here's the far sideline, and now the spectator, this is the person. I'm going to give this fella a hat and some toes. Okay, so the spectator is looking at that through the pane of glass here. Now, the 14 is here. Now, if you notice there that the 14-yard line, this line here, has been found for you really, but look, if it wasn't, I'm going to just do it a slightly longer way there, just to again, you know, show people. So if the spectator looked at the 14 over on the far sideline, here is where it appears on the pane of glass. So if I project that point back down, so that's where it is on the far sideline. So that would be giving me, has to be vanishing to here. So that has to be giving me, that's like, as I said, I already had it anyway, but I'm just showing you how to find it because it has to be vanishing back to there. So we now have the 21-yard line, the 14-yard line. Just label these. So there's 21 and the 14. So now that we have the 14, our next problem is to find the square here, the big square, the large parallelogram. So I want to find these 2 points here. So when the spectator looks at this one, it's here on the glass, and I'll just bring it back one at a time because I don't want to rush through this. So it's here on the glass, and that is that point there. Then likewise, when the spectator looks at the other corner of the parallelogram, it is here on the pane of glass, or the picture plane. So when I project that back, it is there. So they're the 2 corners of the parallelogram, and since the parallelogram, I suppose the hint is in the name really, is parallel, so they are going back towards here. Now if I extended that back, it's going to the vanishing point. The same with this one, if I extended that back, it's going to the vanishing point. So we now have the large parallelogram, so all that remains to be found now is the small one. So they've already found 1 point here, it's already done. So when I project that back, it's here. So I know that this is one end of it. Just draw that light now coming out there, and same thing again, the spectator views, I'm going to find the end of that next, I think. So I'm going to put this in. So the spectator finds that it's here on the glass. So when that's projected back, that is the corner of the small parallelogram. That has to be vanishing over here at this angle, and then the spectator can view the other side of it. It's here on the glass, so I want to project that back in. There's the far side, so I can now heavy this in. I'll put it in blue, so it's going over as far as there, and then it turns parallel to VP2. So small square, as it's called, even though it's not a square. And the final thing here then, now one way that I could find that is using the ground line here, and I'm going to do this in red, and I'm going to just heavy in here the ground line as well. Now if I project a line through the base of the near upright out to the pane of glass, I'm going to put an arrow on that just so you can see. So I'm after projecting from the vanishing point out through the butt of the post or the base of the post, and we are going to find the true height of the goalpost here now on the glass, because anything projected onto the picture plane gives us a true height. So I now need to project the top through the top of the post. I'll just put an arrow on this as well just to help people see it. So I've projected forward through the base of the post onto the ground line here, which is now marking this on the picture plane, so it's going to be a true height. So that here is the bottom and the top, and I think I'll just color that in yellow there to highlight it a bit more. So this here, well, that doesn't come out very good, but this here is the true height, TH for true height, from there to here. I know that's a bit cluttered there now, there's a lot going on there, but so that is that done.